because I want to give a further push uh, to the basic argument that is directly enabled by the book that was written by the great Erwin Schrödinger, and this time I would like to go a little more deep into the argument that's played by Erwin Schrödinger in his book "What Is Life." In fact, he's not giving any biological explanation of what life is, but certainly it does play, and it has played a lot of role in the field of biological science, as well as the chemical sciences. So here I am, and I hope you like the presentation that I'm trying to share with you here. So how Schrodinger's "What Is Life" basically gave birth to the quantum mechanical biology that we have running now, and this thing I'll be sharing with you. I'll be talking about it, and let me see where I can go with this argument. Now, let me begin with a statement that may surprise you. And the statement goes like this: quantum biology did not begin in the laboratory, and it did not begin with lasers or microscopes or the equations. It began basically with a question. Again, the same argument. It was 1944, during the chaos of the World War II. Erwin Schrödinger, the same man who gave us the wave mechanics, asked something that physicists were not supposed to ask. And why does living matter behaves so differently from the dead matter? It's called dead matter. For me, it's not dead. I believe everything has life in it. But here the argument goes like this: even though both are made of the same types of atoms, the biological life and the dead, that question became a small book, what we call as "What Is Life?" And today, I'm standing here as our Father Ross, and I want to go explicitly with some precise examples, and I want to go down. Basically, this book did not merely inspire biology; it prepared the intellectual ground for quantum mechanical biology that is around us in its advanced form. It quietly told scientists that where to look and what to expect. This was, I think, the main argument of the book. And what kind of physics life must obey. So we want to go deeper into this argument. So what Schrödinger did differently here is that before Schrödinger, most scientists, they treated life as some kind of chemistry going on. Chemistry with a lot of complexity in the chemistry, and then certainly molecules plus the chances that could have taken to that complexity, and then reactions between the molecules in some framework of time. Schrödinger basically rejected this framing. He asked a physicist question, not a question from biological point of view. It was not a biologist's question. He did not ask basically, how does life look like? And how does life grow? And maybe how does life change from one state to another state to another state and another state? He asked, how can matter that's obeying the common physical laws maintain order for a long period of time? This shift is crucial basically to understand, to be the basis of a realistic quantum mechanical biology. Because quantum biology exists only because life was reframed as a physical problem. It was not a kind of descriptive one. It's not a kind of description. The first bridge is stability at the atomic scale. It could be taken as the first bridge of life. And Schrödinger made a bold claim here. What he said is that life basically depends on atomic level stability, not just the chemical reactions. At the time, this was seeming very radical kind of argument. Why? Because there was classical physics. Because what classical physics says, the classical physics says atoms vibrate, heat disrupts the order, information, it keeps on decaying, and yet the living cells, they preserve precise structure, reliable memory, accurate replications. Schrödinger basically argued that only quantum rules can explain such kind of stability. And the key contribution that can be taken within this argument of Erwin Schrödinger, what he did is he introduced the idea that the biological order must be protected by the quantum mechanical constraints. They should not be protected by the classical constraints. This single insight later allowed scientists to ask the questions. And what are the questions? Are quantum effects not just present, but functionally used by life? That question is basically what we call today as quantum biology. And again, the argument of aperiodic crystal as a quantum idea. So life in biological form is crystalline in nature, where you have a long range of order of atoms. Schrödinger's most famous contribution, the hereditary material must be an aperiodic crystal. This phrase is often quoted, but really rarely understood. What did he really mean by using the word a crystal quantum stable structure? This is the basic bone of that argument. A periodic, capable of carrying a complex information. Let me put this thing in some other words. If I put this in some other words, life basically stores information in quantum stabilized matter. This idea directly influenced it. It made an impact. It made an action. This idea itself was an audacity. It went through the molecular biology, information theory in the biology, later quantum information analogies. Without this idea, the things that I talked about, scientists would not even think to search for the quantum coherence in the biological molecules. And to take on this argument, to move on from here, The logical steps that I'll be talking about, the Schrodinger's quantum biology. Let me make a connection. Let me try to make an explicit connection so that there is some more kind of understanding over this argument. Schrodinger established three foundations. And what? Life resists disorder in a lawful way. Number two, life depends on atomic precessions. What does that mean? That precession requires a quantum mechanical stability. So quantum biology simply asks us, if quantum laws protect biological order, can the living systems also exploit this quantum mechanical effect? This is not merely a speculation. It's not some kind of mathematical thought going on, a non-mathematical thought going on. This is a direct continuation of Schrodinger's logic that I am trying to force on. If I take an example of photosynthesis, a well-known chemical reaction taking place in plants. Now let's see how Schrodinger's idea became experimental science. In photosynthesis, what we have the light photons, the energy of light, it enters a protein complex that's present in the leaf. Energy must reach a reaction center. And classically, impossible. Classical expectations, energy hopes it will make it randomly, it will go and make it. It has to go. Much energy should be lost in that case. But experiments show us that near perfect efficiency that you have in translating solar energy in some biological energy. We have quantum explanations for that. Energy exists briefly as a wave at that point of time when it hits the leaf of a plant. It explores many paths at one time, and there are interference patterns. These interferences intersect, and then they choose the best path to hit the protein, to hit the atom, to hit a proton. Why is this important? Because Schrodinger argued that life must operate near the limits of physical laws. And photosynthesis does exactly the same thing as is predicted by Erwin Schrodinger. Quantum biology here is not accidental. It is Schrodinger's prediction that's being fulfilled in the name of quantum biology. And there are other arguments that are coming from the same state. The magnetic sensing in the birds. Birds navigate using Earth's magnetic field. Earth has a core, it has a magnetic field. This field is extremely weak. It's a weak magnetic field. And if you go in the framework of classical physics, what classical physics says, that such a weak field should have no effect. Yet birds are accurate in using this magnetic field, which is weak to be sensed. Quantum biology explains this using the spin of an electron, because an electron can have spin up, spin down, can explain it using the flipping of the spin, and quantum correlations between the radicals. So what could we say that Schrodinger's role, what he did, he legitimized the idea that living systems can be sensitive to microscopic physical laws. Without what is life, this idea would have been dismissed as something impossible, something that could not be observed experimentally, that could not be verified experimentally. If I take an example of smell, smell is also a quantum mechanical process. Some smells cannot be explained by molecular shapes alone. And quantum biology suggests us, what it suggests us basically is that electrons, they tunnel odor molecules. As we understand what quantum mechanical tunneling is, an electron can go through a wall of whose energy is greater than that of electron. This idea sounds strange until you remember Schrodinger's core claim. The core claim is again, life uses physical laws in subtle, non-obvious ways. Quantum smell is not a leap, it's a continuation. And why this matters? If you take the same argument to the brain, Schrödinger never basically claimed the mind is quantum mechanical in nature. The argument was never like that. Neither do we say anything like that. But what he said, he insisted that biological order must be physically grounded. Today, if you talk about today, we know neural signaling involves molecular timings. You have ion channels. These channels operate at atomic scales. And quantum biology does not replace neuroscience. It complements it. Again, exactly the bridge here is what Schrödinger basically imagined from his mathematical craziness. And what Schrödinger really gave us, if I would like to summarize that what was the contribution of this beautiful man, Schrödinger did not give answers basically. He's not answering anything in this book. He gave permission. And what he gave permission to apply physics to the life. You can apply physics to a biological life. And search for the quantum order in the warm systems. Why does that order is? Even though the systems are warm, you're not at absolute zero. Treating living matter as low governed, not miraculous. Everything is miraculous. Quantum biology exists because Schrödinger showed that asking such question is not a foolishness. It is necessary. Maybe it would have been taken completely foolishness by arguing this kind of thing. That living objects have order. They take surrounding food to have order, and that order is dispersed in the form of disorder, maintaining the second law of thermodynamics. Now, what is life is not biology. It's not physics. It is a map showing where the laws of matter and the phenomenon of life quietly meet. Quantum biology is simply us, decades later, finally following that map, which was given by Schrödinger. And as Arfad Firdaus, I leave you with the thought, life does not break the laws of physics. Life reveals how deep those laws truly